so let's continue here. Okay, managing growing projects with packages, crates, and modules. As you write large programs, organizing your code will be important because keeping track of your entire program in your head will become impossible. By grouping relative functionality and separating code with distinct features, you will clarify where to find code that implements a particular feature and where to go to change. Okay, this is the program we've written so far have been in one module. As projects grow, you can organize code by splitting in multiple modules and then multiple files. A project can contain multiple binary crates. Okay, one project can contain multiple binary crates and optionally one library crate. As a package grows, a package can contain multiple binary crates, optionally one library crate. As a package grows, you can extract parts into separate crates that become external dependencies. This chapter covers all these techniques for very large projects of a set of interrelated packages that evolve together. Cargo provides workspaces, which we'll cover in the cargo workspaces section in chapter 14. Okay, so there's workspace, there's package, there's crate. Okay, and we need to make sense of all of these. Oh yeah, there they are. In addition to grouping functionality, encapsulating implementation details, let's see, encapsulating implementation details, lets you reuse a code at a higher level. Once you've implemented an operation, other code can call that code via code public interface without knowing how the implementation works. The way you write code defines which parts of public code, which parts are private implementation details that you reserve the right to change. There's another way to limit the amount of detail you have to keep in your head. Okay. Related concept is scope. The nested context in which code is written has a set of names that are defined in scope for reading, writing, compiling codes. Compilers need to know whether a particular name at a particular spot refers to a variable, function, struct, enum, module, constant, or other item, and what that item means. You can create scopes and change which names are in or out of scope. You can't have two items with the same name in the same scope. Tools are available to resolve name conflicts. Okay. Number of features that allow you to manage your code organization, including which details are exposed, which details are private, which names are in each. Okay. Module system. Package, a cargo feature that lets you build, test, and share crates. That's packages. Okay. Crates, a tree of modules that produces a library or executable. Modules and use let you control organization scope and privacy of paths. Path, a way of naming an item such as a struct, function, or module. In this chapter, we'll be covering all these features, discuss how they interact, and explain how to use them to manage scope. By the end, you should have solid understanding of the module system, be able to work with scopes like a pro. Okay, packages and crates. The first part of the module system we cover are packages and crates. A crate is a binary or a library. The crate root is a source file that Rust compiler starts from and makes up the root module of your crate. We'll explain modules in depth in defining modules. Okay, section. A package is one or more crates that provide a set of functionality. A package contains a cargo.toml file that describes how to build those crates. Package contains a cargo.toml file describes how to build those crates. Several rules determine what a package can contain. A package must contain 0 or 1 library crate, and no more. Several rules determine what a package can contain. A package must contain 0 or 1 library crates and no more. It can contain as many binary crates as you'd like, but it must contain at least 1 crate, either library or binary. Let's walk through what happens when you create a package. Okay, cargo new. Cargo new, my project. Created binary application, my project package. ls my project, there's cargo.toml and source directory. Inside the source, there's main. When we entered the command cargo, created a cargo.toml file, giving us a package. Looking at the contents of the cargo.toml, there is no mention of source main because cargo follows the convention that source main is the crate root of a binary crate with the same name as the package. Likewise, cargo knows that if the package directory contains source lib.rs, the package contains a library crate with the same name as the package, and source lib is the crate root. Cargo passes the crate root files to rustc to build the compiler to build the library or the binary. Here we have a package that only contains source main, meaning it only contains the binary crate named my project. If a package contains source main, source lib has 2 crates, a library and a binary, both with the same name as a package. A package can have multiple binary crates by placing files in source bin directory. Each file will be a separate binary crate. A crate will group related, but if it's each directory, okay. A crate will group related functionality together in scope, so the functionality is easy to share between multiple objects. A crate will group related functionality together in a scope, so the functionality is easy to share between multiple objects. For example, rand crate we use in chapter 2 provides functionality that generates random number. We can use that functionality in our project by bringing the rand crate into our project scope. All the functionality provided by the rand crate is accessible through the crate's name, rand. Keeping a crate functionality in its own scope clarifies whether a particular functionality is defined in our crate or the rand crate and prevents potential conflicts. For example, rand crate provides a trait called named RNG. We can also define a struct named RNG in our own crate. Because a crate's functionality is namespace in its own scope, when we add rand as the dependency, the compiler isn't confused about the name RNG refers to in our crate. It refers to the struct RNG that we defined. We would access RNG trait from the rand crate as rand : RNG. What is this : operator called? Scope resolution operator. Scope resolution. Is there a shorthand? Okay. Let's move on and talk about the module system. Defining modules. Defining modules to control scope and privacy. In this section, we'll talk about modules and other parts of the module system, namely paths that allow you to name items. The use keyword that brings a path into scope, and the pub keyword to make it public. We'll also discuss as keyword, external packages, and the glob operator. For now, is it the glob operator? No, it's the glob is the wild card. Okay. For now, let's focus on modules. Modules let us organize code within a crate into groups for readability and easy reuse. Modules also control the privacy of the item, which is whether an item can be used by outside code, public, or an internal implementation detail and not available for outside use, private. As an example, let's write a library crate that provides the functionality of a restaurant. We'll define the signature of a function of functions, but have their bodies empty to concentrate on the organization of the code rather than actually implement a restaurant in code. Okay. In the restaurant industry, some parts of a restaurant referred to as front of the house and other are back of the house. Front of the house where the customers are, where the host seats customer, servers take orders and payment, bartender makes drinks. Back of the house is where chefs cook, work in the kitchen, dishwashers clean up, and managers do administrative work. To structure our crate in the same way that a real restaurant works, we can organize functions into nested modules. Create a new library named restaurant by running cargo new -- lib restaurant, then put the code in listing 7.1 into lib. Let's see. Okay. We define module. So there's module front of the house. There's module housing. Hosting, sorry. Hosting. Add to wait list. Seat at table. Mod serving. Take order, serve order, take payment. We define a module by starting with the keyword mod. Then specify the name of the module, in this case front of house, Place curly brackets around the body of the module. Inside the module, we can have other modules, as in this case, modules hosting and serving. Modules can also hold definitions for other items such as structs, enums, constants, traits, or in listing 7.1 functions. By using modules, we can group related functions together and name why they are related. Programmers using this code would have an easier time finding definitions that they wanted to use because they could navigate the code based on groups rather than having to read through all definitions. Programmers adding new functionality to this code would know where to place the code to keep the program organized. Earlier, we mentioned that source main source libs are crate roots. The reason for their name is that the contents of either of these two form a module named crate at module named crate. At the root of the crate module structure known as module tree. Okay, crate, front of house. Okay. This tree shows how some of the modules nest inside one another. For example, hosting nests inside front of the house. The tree also shows some modules are siblings to each other, meaning they're defined in the same module. Hosting and serving are defined within front of the house. To continue the family of metaphor, if module A is contained inside module B, we say module A is the child of module B, and module B is the parent of module A. Notice that the entire module tree is rooted under the implicit module name crate. The module tree might remind you of the file system directory tree, and on your computer this is a very apt comparison. Just like directories in file system, you use module to organize your code, and just like files in directory, we need a way to find our modules. Okay, path. Path is for referring to an item in the module tree. To show us where to find an item in a module tree, we use a path in the same way we use path when we're navigating file system. If we want to call a function, we need to know its path. A path can take two forms. An absolute path starts from the crate root by using crate name or a literal crate. A relative path starts from the current module and uses self, super, or an identifier in the current module. Both absolute and relative paths are followed by one or more identifiers separated by double columns. Let's return to example listing 7.1. How do we call add to waitlist function? This is the same as asking what is the path of add to waitlist function. Listing 7.3, we simplified our code a bit by removing some of the modules and functions. We'll show two ways to call add to waitlist function from a new function eat at restaurant defined in the crate root. Eat at restaurant defined in the crate root. The eat at restaurant function is part of our library's crate public API, so we mark it with a pub keyword. In the exposing path with pub keyword section, we'll go into more detail about pub. Note that this example won't compile yet, just yet. We'll explain why in a bit. Rust chose to have module system function this way so that hiding inner implementation details is the default way which parse inner code without breaking the outer code. Inner implementation detail is the default. That way you know which part of the inner code you can change without breaking the outer code. But you can expose inner parts of the child module to outer ancestor by using the pub keyword to make public item. Exposing paths pub keyword. Okay. Pub mod housing. Okay. That's still an error because this is private, right? Yeah. Okay. Privacy rule applies. Okay. Pub. Okay. 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 Starting relative paths. Loop. Yeah, starting relative path with super. Super. Okay. Fix order. Super. There are a few extra details. You can also use pub to designate structs and enums public, but there are a few extra details. If you use pub before struct definition, we make the struct public, but the structs field will be private. We can make each field public or not on a case by case basis. What? Didn't they just say, oh, immutable or mutable? Yeah. That's a different one. Mutability. That's gotta suck if every time we need to define it public, everything. Okay. Defined back of house breakfast struct with a public toast field but a private seasonal fruit field. This model is the case in a restaurant where customer can pick type of bread that comes with the meal, but the chef decides which fruit accompanies the meal based on what is in season and in stock. The available fruit changes quickly, so customers can't choose the fruit or even see which fruit they'll get. Yeah, seasonal fruit. Can't see it. Because toast field in the structures public. Eat at restaurant. We can write and read. Okay. Notice that we can't use seasonal fruit field in eat at restaurant because seasonal fruit is private. Try uncommenting the line. Okay. Back of the house breakfast has private field. Needs to provide public associated function that constructs the instance of breakfast. Yeah. We've named it summer. If breakfast didn't have such function, we couldn't create an instance of breakfast in each restaurant because we couldn't set the value. Okay, private. In contrast, if we make an enum public, all of its variants are then public. We only need the public before the enum keyword as shown. Okay. Okay, that's easy. One more situation involving pub that we haven't covered, and it's our last module system features. The use keyword will cover use by itself first, and then we'll show how to combine pub and use. Is it the case that whatever you get in the scope, it also becomes public? Do I have a kanji today? Not yet. Not yet. Yeah. Okay. Okay. Bringing paths into scope with the use keyword. Might seem like paths with we've written function are inconveniently long and repetitive. For example, listing 7-7, whether we choose the absolute or relative path to add to a wasteland. Okay, every time we want it. Okay, I can't function. I'll leave these to tomorrow. I'm in a better I'll reach chapter 13 tomorrow. That's a promise. There's not much here. A little bit here. So vectors, strings, and hash maps. That's the entire programming. Error handling. Okay. Generics. This is heavy. Okay, I'll try to finish the entire thing tomorrow. That's a promise. Okay.